Hello everyone, my name is Kanev. I'm a bachelor student in applied physics at Eindhoven University of Technology, and today I'll present you the work on radio emission from massive stars and exoplanets. So, we know that exoplanets have been traditionally studied in optical and in infrared bands, and that has to do with the most known previous detection methods and technology constraints. However, measurements from those bands do not reveal the full story about exoplanets, and that is the reason why we would also like to look into the radio band. The unique information that radio can tell us has to do with the magnetic field of the exoplanet. Some of the emission mechanisms on the planet itself that emit in radio are directly proportional to the magnetic field strength, and that, together with information about its size, can reveal more about the composition of the planet based on its core. Even if we cannot directly determine the magnetic field, we can still investigate its interaction with the whole star-stellar wind, which will tell us about the atmospheric conditions on the planet and its ability to protect its atmosphere, which is extremely important for habitability. If we want to detect exoplanets in low frequency, we must first understand the source and the strength of their emission. We know that all magnetized solar system planets emit auroral radio emission with its frequency given by 2.8 times the magnetic field strength in Gauss. Knowing that the frequency is proportional to B, some scaling laws indicate that a planet with strong magnetic field close to the star should appear bright in frequencies above the ionospheric cutoff of 10 MHz. Current searches with low FAR are underway, but the sensitivity and beaming geometry might prove that to be very challenging. Even if we did have perfect instruments, because we're dealing with point sources, exoplanetary emission might be confused with emission from other stellar sources. Therefore, understanding the emission of stars in low-frequency radio domain is crucial for correctly identifying exoplanets when the time comes. So, in order to do that, our project focuses on massive stars. They have been extensively investigated in higher frequencies, but not so much in lower frequencies. All massive stars have strong ionized winds, and we expect that thermal free emission in radio is common from those stars. In the case of binary systems, the strong winds between the stars create shocks that can later accelerate electrons and thereby creating synchrotron emission. Those are some examples of why massive stars might appear in radio, but the main focus on our project is to correctly characterize the type of emission from those radio bright stars. So, how do we do that? From selected O and Wolf-Rayet type stars optical surveys, we have compiled a master catalog of 849 galactic stars. We plan to cross-match those stars with our low-frequency survey, LOFAR at 150 MHz. This will be our main investigation, but because we would also like to see spectral properties, we also look at other higher frequency instruments, such as ASCAP at 887.5 and VLA at 2 and at 4 GHz. Our preliminary results show 9 unique matches with LOFAR. At first, 9 matches out of those 849 stars seemed surprisingly low. We looked at the chance coincidence rates by choosing appropriate matching radiuses, but only after rerunning the cross matches with ASCAP and with VLA, we started to notice a trend. We found more matches at higher frequencies. From the theory alone on massive stars, we know that their strong winds should produce thermal free emission. At low frequencies, however, the signal becomes too faint, which partly explains the trend that we're seeing. Another detection mechanisms might be synchrotron emission, but because that only happens in binary systems and under special conditions, it is more rare. The low detection fraction tells us about which stellar configurations are capable of producing bright low-frequency radio emission. And our plan is to correctly characterize the emission mechanisms out of all the sources and look for trends. By identifying which stars emit and understanding the underlying emission mechanisms, we can establish the types of stellar environments that could possibly mimic planetary signals. So, our work continues. and I thank you for watching.